The problem is this. What does the electric field look like in the domain of -10 to 10 meters and the range -10 to 10 meters, where one object with a radius of 1 meter at the origin has a charge of 30 times 10 to the -7th coulombs, a second object with a radius of half a meter at the position 720 has a charge of 10 to the -7th coulombs, and a third object with a radius of 0.75 meters at the position -540 has a charge of 10 times 10 to the -7th coulombs. I'm going to use GlowScript to illustrate this. First, I need to define my three objects. I will label the first as ball 1 and set its position, radius, and color for the sake of differentiating it. Next, I will attribute the charge to ball 1 and label this attribute ball1.q for future reference. I will repeat this process for the remaining objects, which I will label ball 2 and ball 3. Next, because we are calculating the electric field, I'm going to define Coulomb's law constant as Kc. Also, I will define a small scaling factor, SCF, as 0.002, so that the arrows I will put in the field won't look like a mess. Now, I will define a for loop, which will be able to produce iterations of electric field vectors at each point in my domain and range. I will set the domain from -10 to 10 with increments of 1, so that the final picture won't look too crowded with arrows. So that a grid is created, I will set the range from -10 to 10 within this domain. I'm setting up vectors for each of the electric fields coming out of the objects, denoted R1, R2, and R3, at every defined point on the grid. For example, the electric field of object 1 at any given point within the grid is given by the difference between the vector to that point in space and the position vector of the first object. This is repeated for objects 2 and 3. Because these three charged objects constitute a system of charges, I'm applying the superposition principle to find the net electric field at any point in the grid. Here, the electric field created by the first object is given as Coulomb's constant times the object's charge times the unit vector of R1 over the magnitude of R1 squared. This electric field is added to the electric fields generated by the second and third objects to give us the net field. Finally, so that we can actually see what the field looks like, all the E-field vectors in the grid will have arrows assigned to them. The arrow will start at the point, making its position, the arrow will start at the given point, making its position equal to I, j, 0. The tip of the arrow will extend to the electric field experienced at that position multiplied by a scalar factor, so that the arrow can fit in the screen. I'm setting a small shaft width for the arrow for the same reason. Then, when I run the program, I get this grid of vectors expressing the net electric field at those points. As expected, the vectors coming out of the first object, aka the blue ball, are the largest in magnitude because they had the largest charge. Quickly, the vectors get smaller and smaller the further away points are from the system of charges, and where two or more electric fields act on a single point, the result is a vector sum.